the king's advisor, Arbegla, is watching all of this discourse between you, the king, and the bird, and he's starting to feel a little bit jealous because he's supposed to be the wise man in the kingdom, the king's closest advisor. So he steps in and says, okay, if you and this bird are so smart, how about you tackle the riddle of the fruit prices? And the king says, yes, that is something that we haven't been able to figure out, the fruit prices. Arbegla, tell them the riddle of the fruit prices. And so Arbegla says, well, we've want to keep track of how much our fruit costs, but we forgot to actually log how much it cost when we went to the market. But we know how much in total we spent. We know how much we got. We know that 1 week ago, when we went to the fruit market, we bought two pounds of apples. We brought 2 pounds of apples and 1 pound of bananas. 1 pound, I guess I can, 1 pound of bananas. And the total cost that time was $3. So there was a $3 in total cost. And then when we went the time before that, we bought 6 pounds of bananas, 6 pounds of apples, I should say. 6 pounds of apples and 3 pounds of bananas, and the total cost at that point was $15. So what is the cost of apples and bananas? So you look at the bird looks at you. The bird whispers into the king's ear, and the king says, well, the bird says, well, just start defining some variables here so we can express this thing algebraically. So you go about doing that. What we want to figure out is the cost of apples and the cost of bananas per pound. So we set some variables. So let's let A equal the cost of apples per pound, and let's let B equal the cost of bananas per pound. So how could we interpret this first information right over here? 2 pounds of apples and a pound of bananas cost $3. Well, how much are the apples going to cost? Well, it's going to cost 2 pounds times the cost per pound times A. That's going to be the total cost of the apples in this scenario. And what's the total cost of the bananas? Well, it's 1 pound times the cost per pound. So you're just going to have B. That's going to be the total cost of the bananas because we know we bought 1 pound. So the total cost of the apples and bananas are going to be 2A plus B. And we know what that total cost is. It is $3. Now let's do the same thing for the other time that we went to the market. 6 pounds of apples, the total cost is going to be 6 pounds times $1 per pound. And the total cost of bananas is going to be, well, we bought 3 pounds of bananas, and the cost per pound is B. And so the total cost of the apples and bananas, this scenario, is going to be equal to $15. So let's think about how we might want to solve it. We could use elimination, we could use substitution, whatever we want. We could even do it graphically. Let's try it first with elimination. So the first thing I might want to do is maybe I want to eliminate, let's say I want to eliminate the A variable right over here. So I have 2A over here, I have 6A over here. So if I multiplied this entire white equation by -3, then this 2A would become a -6A, and then it might be able to cancel out with that. So let me do that. Let me multiply this entire equation, the entire equation times -3. Times -3. So -3 times 2A is -6A. -3 times B is -3B. And then -3 times 3 is -9. And now we can essentially add the two equations, or add the left side of this equation to the left side of that, and the right side of this equation to the right side of that. We're essentially adding the same thing to both sides of this green equation, because we know that this is equal to that. So let's do that. Let's do it. So on the left-hand side, 6A and 6A cancel out. But something else interesting happens. The 3B and the 3B cancels out as well. So we're just left with 0 on the left-hand side. And on the right-hand side, what do we have? 15 minus 9 is equal to 6. So we get this bizarre statement. All of our variables have gone away, and we're left with this bizarre, nonsensical statement that 0 is equal to 6, which we know is definitely not the case. So what's going on over here? What's going on? And then you say what's going on, and you look at the bird, because the bird seems to be the most knowledgeable person in the room, or at least the most knowledgeable vertebrate in the room. And so the bird whispers into the king's ear, and the king says, well, he says that there's no solution, and you should at least try to graph it to see why. And so you say, well, the bird seems to know what he's talking about, so let me attempt to graph these two equations and see what's going on. And so what you do is you take each of the equation, and when you graph it, you like to put it in kind of the y-intercept form or slope-intercept form. And so you do that. So you say, well, let me solve both of these for b. So if you want to solve this first equation for b, you just subtract 2a from both sides. If you subtract 2a from both sides of this first equation, you get b is equal to negative 2a plus 3. Now let's solve this second equation for b. So the first thing you might want to do is subtract 6a from both sides. So you would get, I'll do it right over, let me do it right over here. You would get 3b is equal to negative 6a plus 15. And then you can divide both sides by 3. You get b is equal to negative 2a plus 5. So the second equation, let me revert back to that other shade of green, is b is equal to negative 2a plus 5. And we haven't even graphed it yet, but it looks like something interesting is going on. They both have the exact same slope when you solve for b, but they seem to have different, I guess you could call them b-intercepts. Let's graph it to actually see what's going on. So let me draw some axes over here. So that is let's call that my b-axis, and then this could be my a-axis. And this first equation has a b-intercept of positive 3. So let's see, 1, 2, 3, 4, 5. The first one has a b-intercept of positive 3, and then has a slope of negative 2. So you go down, or you go to the right one, you go down 2. Go to the right one, you go down 2. So the line looks something like this. I'm trying my best to draw it straight. So it looks something like that. And now let's draw this green one. This green one, our b-intercept is 5, so it's right over here. But we have the exact same slope, a slope of negative 2. So it looks something like that right over there. And you immediately see now that the bird was right. There is no solution because these two constraints represent or can be represented by lines that don't intersect. So the lines don't intersect. They don't intersect. And so the bird is right. There's no solution. There's no x and y that can make this statement equal true, or that can make 0 equal 6. There is no overlap between these two things. And so something gets into your brain. You realize that Arbeigla is trying to stump you. And you say, Arbeigla, you have given me inconsistent information. This is an inconsistent system of equations. Inconsistent, which happens to be the word that is sometimes used to refer to a system that has no solutions, where the lines do not intersect. And therefore, this information is incorrect. We cannot assume that the apple or banana, either you're lying, which is possible, or you accounted for it wrong, or maybe the prices of apples and bananas actually changed between the two visits to the market. At which point, the bird whispered into the king's ear and says, oh, this character isn't so bad at this algebra stuff.